Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we're taking a proper deep dive into a really foundational concept that unlocks all of Unit 6, electromagnetic induction. We're talking about magnetic flux. And our promise is simple, to give you a framework that is so clear, so easy to remember that it becomes perfectly safe for your exams. Okay, so let's just jump right in. Let's try to unpack this central mystery of electromagnetic induction, or EI as we call it. It's one of those topics in physics that, it almost seems to defy common sense. Think about it. You have a simple conducting loop, like a coil of wire, and a magnet. Now, if you push that magnet towards the coil, we all know that electricity, a current, is somehow generated in that coil. But here's the puzzle. They are not touching, and you haven't plugged the coil into any battery, so no physical contact, no power source. How on earth is a current being pushed through those wires?
Exactly. That's the thing that always feels a bit like magic. We spend years learning that current needs a battery, a potential difference, some kind of energy source. And then suddenly we're told just moving a magnet nearby creates electrical energy almost from nothing. It is genuinely confusing.
And that confusion is precisely what makes the original experiment so brilliant. See, everyone's first guess is that motion is the key, the relative movement between the magnet and the coil. And yes, most of the time, motion is involved. Think about an AC generator, for example. But here's where it gets really, really interesting. This is a surprising fact that Faraday and Henry established. You do not absolutely need motion.
Wait, hold on. You're saying motion is not essential. But every demonstration in school shows the magnet moving back and forth.
That's just one way to do it. The real requirement is simpler and also more profound. It's just change. Consider this setup. You have two coils, coil 1 and coil 2, just sitting next to each other. Perfectly stationary.
Okay, no movement at all.
No movement. Now, coil 1 is connected to a galvanometer to detect current. Coil 2 is connected to a battery with a simple switch. When you press the switch on coil 2, its current jumps from 0 to maximum almost instantly.
Right, so the magnetic field created by coil 2 also appears and grows very, very quickly, even though nothing has physically moved.
Precisely. And in that tiny momentary interval, just for a fraction of a second while that field is changing, the galvanometer on the stationary coil 1 suddenly picks. It shows a brief current.
Wow. So
Yeah.
the change in current in one coil induces a current in the other, even when they're both at rest. That means we need some way to measure how the magnetic field from one thing links with the other, a way to quantify that connection through empty space.
That is the entire point. That momentary current, produced without any motion, proved that the key physical quantity is not movement itself, but the rate of change of something called magnetic flux. This flux is the bridge. It's what links the changing field of coil 2 to the resulting current in coil 1. So let's get straight to the core idea. What is this magnetic flux, really? At a zero level, forget the formulas for a second. It's just a measure, a number that tells you how much of the magnetic field actually passes through a given surface. It quantifies that linkage. And to make this completely intuitive, let's use an analogy. Imagine magnetic flux is like the amount of rain passing through your window.
Okay, rain through a window. I can picture that. How does that connect to the physics?
It maps perfectly. First, you have the magnetic field strength, B. In our analogy, that's just the intensity of the rain. If it's raining harder, more water comes through the window, right?
Right. Stronger B, more flux. Makes sense.
Second, you have the area, A. That's the size of your window. If you have a bigger window, more rain comes in, even if the rain intensity is the same.
Okay, so larger area A, more flux. That's also straightforward, strength and size. But what about the third factor? The orientation is always the tricky one.
Ah, yes. And it's the most critical one. That is the angle, theta. So imagine the rain is falling straight down. If your window is horizontal, like a skylight, it catches the maximum amount of rain. That's maximum flux. But what if you tilt that window?
Then less water passes through it.
Exactly.
Yeah.
And if you tilt it until it's perfectly vertical, the raindrops just skim past the surface. Almost nothing comes through.
So even with heavy rain, strong B, and a huge window, large A, if the orientation is wrong, the flux can drop to 0. The angle can completely override the other two factors.
Precisely. It's the combined effect of the field, the area, and the orientation that gives you the total linkage.
But that brings up a really important doubt. Why do we need to combine them all into this one thing called magnetic flux? Why can't we just track B, A, and the angle separately? Why is creating this single number flux so important?
That is a brilliant question. It gets to the very heart of why the concept was invented. See, Faraday needed one single quantity to describe the total interaction. Imagine writing a law of physics. You need a formula where the induced current depends on what? Sometimes the field gets stronger, sometimes the loop gets bigger, sometimes the loop just rotates. Flux exists to compress all three of these possible changes into one single number. It simplifies the mathematics beautifully. Faraday's law says the induced EMF is proportional to the rate of change of this one quantity, flux, regardless of what caused the change. It's the universal measure of linkage. Now let's build a really strong mental image for this. Picture a rectangular loop of wire, and it's sitting in a uniform magnetic field that's pointing straight up. Imagine the field lines are like thousands of parallel threads going upwards. If the loop is lying flat on a table, its surface is perpendicular to the field lines. Lots of threads will pierce right through. You have a large flux.
And what happens if we start to rotate the loop? Say we lift one edge up?
As you slowly rotate it, you can see that fewer and fewer of those threads are able to pass through the opening. And when the loop is standing perfectly upright, parallel to the threads, the lines just glide past its edges. Effectively, zero lines pass through it. The flux is now zero. That very change from maximum flux to zero flux, just by rotating, is the fundamental principle of an AC generator. The rotation constantly changes the angle, which constantly changes the flux, which creates a continuous current. Okay, so now that we have the intuitive idea locked in, let's bridge this to the formal exam-ready definitions. We need to see how NSERT formally defines magnetic flux.
Right. I had the textbook definition here. I'll read it exactly as it's written. Magnetic flux through a plane of area A placed in a uniform magnetic field. B can be written as AB, A cos A, where A is angle between B and A. The SI unit of magnetic flux is Weber, WB, or Tesla meter squared, TMB. Magnetic flux is a scalar quantity. Okay, so the formula is BA cos theta. But the definition says the angle between B and A. A is area. It's a size. How can a size have an angle with a field? What is this area vector A?
That is the number one point of confusion. So let's slow down and get this absolutely right. We treat the area of the coil, A, not just as a number, but as a vector, the area vector. And the direction of this area vector, by definition, is always normal or perpendicular to the surface of the coil.
Oh, okay. So if my coil is lying flat on the table, the surface is horizontal. That means the area vector A is pointing straight up, perpendicular to the table.
Correct. Now, let's say your magnetic field B is also pointing straight up. In that case, what's the angle between the B vector and your A vector?
Well, they're both pointing up, so they're parallel. The angle between them is 0 degrees.
Perfect. Theta is 0. And what is cos of 0?
1.
Exactly. So the flux formula, BA cos theta, just becomes BA. Maximum flux. It matches our mental picture perfectly.
That makes so much more sense. So if the coil is standing vertically, but the field B is still pointing up, then the area vector A is now pointing horizontally, and B is pointing vertically. They're perpendicular.
Right. So theta is 90 degrees, and cos of 90 is
0. The flux is 0.
Yes. The math now confirms our rain analogy. The cos theta term is the mathematical tool that captures the geometry. It tells you how much of the area is effectively seen by the field. And because it's a scalar dot product, the final result, flux, is a scalar quantity. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's do a very quick, minimal example with numbers just to anchor the unit. Let's say we have a magnetic field, B equals 0.5 Tesla, and a small coil with an area A equals 0.02 square meters. We place it for maximum linkage, so the B field is parallel to the area vector.
Okay, so theta is 0, cos theta is 1. The flux is just B times A.
Yes, just multiply them. 0.5 times 0.0.
That gives 0.01. The unit is Weber, right? So
Yep.
0.01 Weber?
Exactly, 0.01 Willy B. But now comes the think part. This 0.01 Willy B value is just a snapshot, an instantaneous value. If this value stays constant, nothing happens. But if we now rotate that loop so that the flux changes, say it goes from 0.01 Willy B down to 0 Willy B in 0.1 seconds, that change is what produces the current. And this is the ultimate connection to the rest of the chapter. Magnetic flux is the quantitative link. Anytime you have a time-varying flux, which means det is not 0.
Then you get an induced EMF, according to Faraday's law.
You get an induced EMF. It doesn't matter if B is changing or A is changing or theta is changing. If the flux changes, you get electricity. All right. Now let's talk about the silent killers. These are those small, innocent-looking mistakes that can wipe out your marks in the board exams. Misconception number 1. Many students think that magnetic flux depends only on the magnetic field, B.
Yeah, that makes sense. Because you think, well, it's a magnetic field, B is the main thing. If B is 0, flux is 0. So you focus on that.
Exactly. But the correct idea, and you have to burn this into your mind, is that flux depends equally and crucially on the area, and most importantly, the angle. You can have a massive B field, a huge area, but if your angle is 90 degrees, your flux is 0. The little hook to remember this is field, face, and tilt together decide flux. Okay, misconception number 2, the steady field trap. Students see a strong stationary magnet next to a stationary loop, and they assume there must be a current.
They're confusing the mere presence of a magnetic field with the process of induction itself.
Precisely. The correct idea is that a constant steady flux induces 0 EMF. The system has to be dynamic. A changing flux is absolutely necessary. It's the rate of change that matters, not the value itself.
So, just to be 100% clear, if I have a very powerful 10 Tesla magnet, but I hold it perfectly still next to a coil, the induced current is 0. Because the flux, while large, is not changing. The key word is change.
That is the perfect way to state it. You've completely understood the difference. Now, let's just lock this in with a few memory anchors so it sticks during exam pressure. First, for the formula, A equals BA cos theta. The mnemonic is simply BA cos for flux. Say it a few times, it will stick. BA cos for flux. For the concept of rotation changing the linkage, remember the phrase, turn the loop, lose the flux. It connects the action to the result. And finally, a physical gesture. I want you to actually try this. Hold a notebook in front of you. That's your coil. Now imagine a beam of light is hitting it from the front. That's your magnetic field. When the notebook's face is perpendicular to the light, maximum light hits it. Maximum flux. Now slowly twist the notebook until it's edge onto the light. You see how the light just skims past, the flux becomes 0? That physical twisting motion will help you remember the importance of the angle, theta. Okay. To bring this entire deep dive to a close, let's summarize with 3 key exam-safe points that you must carry with you. 1. Magnetic flux A cos B is defined as the scalar product BA cos theta. It measures how strongly a magnetic field links a surface, depending on field, area, and angle. 2. Flux is a scalar quantity. It only has a magnitude. Its SI unit is the Weber, which is Webby-Ebby, or you can also write it as Tesla meter squared. And number 3, the most critical point. The induced M in electromagnetic induction is always proportional to the time rate of change of magnetic flux, which we write as det. Remember, no change in flux, no current in the circuit. To get maximum marks in 12th CBSE physics, chemistry, and maths, visit ProfSam.com.
That is PROFSAM.
Yes, ProfSam.com. We really hope this session on magnetic flux has brought you absolute clarity. Study smart, and we will catch you in the next deep dive.